So with chapter 10 being circles, you're not going to be just forgetting about your triangle stuff, right? We're still going to use that. Okay? We're still going to use our triangle stuff. So don't just let that fall out of your mind. We're actually going to use some of it today still. So we're going to be using it right away, and we're going to continue to use it. 10.1 is tangents to circles. Now, you are going to see me. I'm going to start abbreviating the word circles like that. So be aware of that. You feel free to do that also. If you want to abbreviate the circle just like that, do it. The book is going to do that as well. So with circles, there's already some stuff that you already know. And I know you already know that stuff, but we're still going to go back over it real quick. The first thing actually that you might not know, or that you might not have heard, not the first part, this is the center point. Why would they call it the center point? It's in the middle, it's in the center of the circle, right? That's the center point. Now the part that you might not know is if that center point is called point P, the name of this circle is circle P. Now, you might not have known that, but I'm guessing if I would have drawn that up there and started talking about that circle as circle P, you probably would have figured that out pretty quickly, right? That's not a difficult concept for us. I think you could have done that. So center point, if it's point P, it's circle P. If it's point Z, it's circle Z, whatever it be. I also know that most of you, hopefully all of you, know that that would be called a what? That is a diameter. Why? Because it goes all the way across and goes through the center point. Does a diameter have to go through a center point? Yes, it does. So there's my diameter, because it goes from one side of the circle to the other through the center point. We'll go ahead and label that. And this is a radius. And a radius goes from where to where? The center point to the circle, right? To the edge of that circle. We're going to come to this later, so I'm just going to ask you real quick. You don't need to draw this. Are those two radius or radii the same length? Yeah, always, right? And if I drew another diameter, it would be the same length as the other diameter, right? So just keep that in mind for a problem that we're going to do towards the end of class. Let's look here. All right. Our new terms. This stuff I would have expected you to already know, and hopefully you did. Our new terms. First one is a chord. A chord is a segment whose endpoints lie on the circle. A segment whose endpoints lie on the circle. So, is this a chord? Yeah, that's a chord. Does it matter where at on the circle it is? No, as long as both endpoints are on the circle, it doesn't matter where at exactly it would be. Is a diameter a chord? Yeah, the endpoints of a diameter are both on the circle, aren't they? What about a radius? No, because only one point is on the circle, right? Okay. Questions on a chord. That might be a new term for you guys. The next new term that we have is a secant. A secant is a line. It says a line. It could be a segment. Okay, so be aware of that. But they say a line which intersects a circle in 2 points. Seems to be close to the same thing as a chord, right? Okay, we know it intersects in 2 points. The difference is a secant extends outside of the circle. A chord does not. A chord stays inside the circle. Okay, now we've been talking in the last few class periods. You do have to be careful. Okay, let's say these are points A and B. If they told me this, I would name that a secant. Right? Everybody agree with that? Okay. But if they told me this, that's a chord. Does everybody see the difference in these two? This is but it's talking about a line, right? This is talking about a segment. Okay? So line AB is a secant, segment AB is a chord. Yes.
But when you said that, it could be like a segment.
So, okay. What that means is maybe you have point C and point D. DC is a secant because it extends outside of the circle. Does that answer your question? Okay. Yeah, Royal. A secant contains a chord, but is not a chord. Good question. Okay. A secant is not a chord, but it does contain a chord. Okay. The last new one that we have here is a tangent. Now, this isn't the same tangent we've been talking about. Okay, this doesn't mean opposite over adjacent right now. Okay, I don't want you to forget those things. Okay, because that's going to be useful information. Okay, but this is different. When we're talking about circles and we use the word tangent, it is a line which intersects a circle at one point. Does that mean 2 points? Does that mean 0 points? No, exactly 1 point. Okay. This would be an example of a tangent. That line intersects the circle in exactly one point. Lainey? It could be a segment. Is that what you're asking? Yeah, it might be a segment. Maybe it's segment like this, right? Yeah, that could be. That segment would be tangent to the circle. Yep. Royal?
What about one that just like starts in the middle of the circle and goes out?
Like a radius?
Yeah, but
It has to, that's a good question, has to be outside the circle for it to be a tangent. Okay, it can't go inside of it. Good question though.
so radius isn't.
A radius is not a tangent, correct? Now, is it technically tangent to the circle because it intersects at one point? Yes, technically. But we wouldn't consider a radius a tangent. Okay? Alright, so we've had some new definitions, some old definitions. Hey, radius, diameter. Excuse me, we already knew those, right? Okay, but now you have chord, secant, tangent. Okay? Try not to confuse those three. Okay? You might have to study those a little bit to get those mastered. Okay, hopefully we'll have them by the end of the day. I want you guys to take a look down at example 1. Okay, the directions tell us, they say, tell whether the line or segment is best described as a chord, a secant, a tangent, a diameter, or a radius of circle C. Okay. So, again, ignore the solutions. We don't want to look at those. We can figure this out on our own. Raise your hand when you can tell me, what is AD? Lainey, what's AD? AD is a diameter. Why? It goes all the way across the circle. Now, technically, is it a chord? Yes. But, are all diameters chords? Yes. So which one is more specific? Telling me it's a diameter or telling me it's a chord? Telling me it's a diameter. Okay, that's much more specific. So that's what I want you to do. If it's a diameter, tell me it's a diameter. Okay, don't just call it a chord for me. What about CD? CD. Gavin? That would be a radius. Okay, because it goes from the center point to the circle, right? Okay. And line EG. Got to be careful with that one. Line EG, Travis. That would be a tangent. Reason? It intersects the circle at exactly one point. Good. And the last one, Royal, is HB. That is a chord. Why is that not a secant? Right. Now, they told me this, and it was a chord, right? What if they would have told me this? It would have been a secant, right? Okay, so be careful. Or even if they would have told me this, that would be a secant. It's the same segment, right? But G is outside the circle, K is outside the circle. So that actually passes all the way through, correct? Okay, so be aware of that. If it passes all the way through, it is going to be a secant. Go ahead, Lainey. Got a question? Sure? Okay. Alright. Go ahead and flip the page. Okay, we got some more new information. Alright. We know that tangent means what?
One.
1 point of intersection. Intersects at 1 point, right? Could I draw two circles that are tangent to each other? Could I draw two circles that intersect at 1 point? Could I draw two circles that intersect at 2 points? Could I draw two circles that don't intersect at all? Yeah. Okay, so we're going to go through all those scenarios. Okay, first one intersects at 2 points, would look something like that. Okay, we don't really have a name for that. We just know that there's 2 points of intersection. Are they tangent to each other? No, absolutely not, because there's 2 points of intersection. Okay? Tangent means 1 point of intersection. Are these two circles tangent to each other? Those only intersect at one place, right? Okay. Those two circles are what we would call internally tangent to each other. Okay, those circles are internally tangent. Can anybody give me a reason why we would call it that? One's inside the other, right? Internal. Okay, so those two circles are internally tangent, which would make you assume that those circles are externally tangent. Good. Makes sense, right? Okay, this is going to get confusing in a second. So bear with me. Make sure you have this down. Internally tangent, because one's inside the other. Externally tangent, because they're both on the outside of each other, right? Okay. Now I'm actually going to scroll back up to right here and put one in here that these are actually called concentric circles. What do you suppose concentric means then? Close. Not just no points of intersection. What else is special about those two? Royal? Yeah. They share the same center point. Okay, that's what I was looking for. You're right, though. They are, but that's not what concentric means. Concentric means they share the same center point. Okay? You can kind of see the word center in there, right? Okay? Concentric, they share the same center point. Okay? These are the big ones. Internally tangent, externally tangent, correct? Okay. Now I'm going to confuse you. You ready? Okay. What do you suppose a common tangent is? Okay, close. A common tangent would be a line, kind of. Taylor? Go ahead. Right, so it's going to be a line which is tangent to two circles, right? Okay. A common tangent or common tangents is going to be a line or lines which is tangent to two circles. Okay. So, if I had two circles, would that be a common tangent? Yeah. Would that be a common tangent? As long as I had it drawn correctly, it would be, right? Okay. Those are common tangents, correct? They're tangent to two circles. Now, this, or these red lines, are called common internal tangents. Anybody seeing the confusion I'm talking about between the last thing we talked about?
Yeah, they're not inside.
These are common internal tangents. These two circles are internally tangent. See the play on words? Okay, you got to be careful, don't you? These two circles are internally tangent to each other. These two circles share common internal tangents. Okay, just be very careful on the wording. Are these two circles internally tangent to each other? No, they're not. They don't even intersect each other. Okay? But they do share common internal tangents. Okay? These are common, I don't know where to write it at. External tangents. Are the circles externally tangent to each other? No. But they share common external tangents. Okay? So these are common external tangents. These two circles are externally tangent to each other. Okay, so just be careful on the play on words there. Now, how am I going to remember that these are internal tangents and these are external tangents? Yeah, if they go in between, they are internal. If they stay on the outside or the exterior, they are external. Okay, now the book does it a different way, so if you like the way the book does it, that's fine. They say that if you draw a segment from center point to center point and the tangents intersect, then they're internal tangents. And that if you draw from center point to center point and they don't intersect, they're external tangents. Okay, however you want to remember that is fine by me. I don't care. I just need you to be able to remember it. Okay? I personally like to think if they're in between, they're internal. If they're exterior or on the outside, they're external. Okay, well, like I said, however you have to remember that is fine by me. We doing all right? Okay. Now the next part, I don't expect you to write down because I'm going to really, really, really hope that you already know this. The next two definitions are interior of a circle and exterior of a circle. Where's the interior at? Right there, right? Inside. Exterior is outside. Hopefully you know that. Okay, the exact definitions literally say interior of a circle consists of the points that are inside the circle. Exterior of a circle consists of the points outside the circle. Again, I think you guys are all bright enough to know that, right? Okay. Alright, so we're going to bypass that. If I asked you what a point of tangency is, what would you tell me? Okay, but a point of tangency, that would be a tangent. What is a point of tangency? Yeah, it's where it intersects, right? So, is this a point of tangency? Is that? Is that? 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 Yeah, those are all points of tangency, right? It's where things are tangent to each other at. Okay? So, with that, we actually have two theorems. So if you have your theorem sheets, please get those out. Okay. We're going to name, they don't have names, we're going to name them both tangents to a circle, and then we're just going to number them theorems 1 and 2. Because you're not going to do these in proofs, we're just using it to solve. Okay. Everybody ready? All right. If a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. If a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. Okay. So what that means is with our circle, if I have line L, I have a Q here, a P here. First of all, what's the name of that circle?
Q.
Circle Q, right? Okay. So if L is tangent to circle Q, then L is perpendicular to QP. Okay, and perpendicular means what? Yeah, it forms right angles. Okay. So, if I know something is tangent, then I know it forms a right angle, right? With the radius. So this would be a right angle, right? How are we going to use that? Why? Who cares?
Triangles.
Yep. We're going to make triangles out of it. What kind of triangles? We're going to make right triangles out of it. Okay? So just be aware of that. You don't need to draw that up there if you don't want to. Okay? But be aware of that. That's why we're learning this, is so we can form right triangles. It's going to help us solve things out. Okay. Second theorem is just the converse of that. Okay, so it's basically saying the same thing, but backwards. Okay, if a line is perpendicular to a radius of a circle, and its endpoint, at its endpoint on the circle, then it is tangent to the circle. If a line is perpendicular to the radius of a circle at its endpoint on the circle, then it is tangent to the circle. Okay. Again, that's just saying the same thing backwards. Okay. We'll use the same stuff. That's Q, P, L. It says that the line is perpendicular. Okay. So if L is perpendicular to PQ, then L is tangent to circle Q. Okay, it's just the converse there. So if it's tangent, it forms a right angle with the radius, right? And if it forms a right angle with the radius, then it must be tangent, right? Okay, just converse of each other. Alright, so there's a couple ways we can use this. Okay, let's go ahead and say I have my circle. I have my center point A. Goes up to point B. Over here to point C. This is 11, 43, and 45. What? AC wouldn't be anything. Nothing that we learned, right? Okay. They want to know, or they want you to verify that BC is tangent to circle A. Well, if it's tangent, what has to be true? Right, that right there has to be a right angle, right? So that triangle has to be a right triangle. Okay, these are nearly exact problems that you just did on your test yesterday. You should be able to figure out if that's a right triangle, shouldn't you? How do you do that? Yeah, Pythagorean theorem, okay? Even just because it has a circle doesn't mean things change. Okay, you can still do Pythagorean theorem and figure out if that's a right angle or not. How would I set that up, Taylor Arnett? Okay, and most of you would probably put that on the other side. This is how the book sets it up usually, though. Okay, probably gonna need a calculator, right? Anybody got 45 squared for me? 2025 equals 11 squared is 121. What's that one? 43 squared. 1,849. Okay, so then I get 2025 equals 0. Is that a right triangle? No. So, if it's not a right triangle, is BC tangent to circle A? No, it is not. Okay, so BC is not tangent to circle A. Can everybody agree with that? Based on our theorem, right? To be tangent, it would have to form a right angle. Alright, we got 8 minutes here. We have one more problem that I want to get done here for us. Okay, we have another circle. We know that basically what it tells us is we have a water tower and we are standing 14 feet from the edge of the water tower. So from here to here is 14 feet. And from that point, it is 28 feet to the point of tangency. Okay? So I'll just put some letters up here. Is BC tangent to the water tower? If they said C is 28 feet from the point of tangency. Yes. Okay? So it has to be tangent because they use the word point of tangency, right? Okay? So if it's tangent, what else do you know? You know that B is a right angle. Or that ABC is a right triangle, correct? Okay? They want to know what is the radius of the water tower. Now, obviously, you can't just hop inside the water tower and measure that out. You agree with that? Okay. What do you know, Royal? Okay. But, Jacob, 1 second. Okay, I like your idea, but we don't know any angle measures. Okay? What do you know about these two segments? Why are they the same? Their radius. Remember me saying that almost the very first thing we talked about? And now it's the very last thing, and we're still using that. Okay? Those two things are the same thing, right? So when you plug in variables, do you want to make them different variables? No, because they're the same. Okay, so it wouldn't make any sense to make things that are the same different variables, correct? Okay? So, Royal, I am with you. We do need to use Pythagorean theorem. If I would have had two different variables, you wouldn't be able to solve this. Okay? Because with two different variables, you would have an x and a y in the Pythagorean theorem. Okay, that's not okay. Okay, when we do Pythagorean theorem, if we have one variable, we can figure out what that equals, right? Okay, so let's go ahead and try to set this up. What's A? 28 feet? Or 28 squared? What's B? X squared. Equals, now this is where you got to be careful, x plus 14, because I need the whole length of AC, right? So that's x plus 14 squared. And now this side we should be able to handle. What's 28 squared? Somebody with the calculator. 784? Plus x squared equals, this is where it gets tricky. Don't tell me that's x squared plus whatever 14 squared is. Okay, what does it mean to square something? Multiply it by itself. So that means I need to take x plus 14 and multiply it by x plus 14. How do I multiply those two things together? kinda. Foil. I think the exact words of a student in first period is, you got to use that foil garbage. Okay? You can call it what you want. If you may think it's garbage, I don't know. Okay, but you have to use it here. Okay? Because this is not x squared plus 14 squared. That's not what that is. Okay? You do have to FOIL. So you do first, outer, inner, last, right? Okay? What do I get first? X squared plus plus. Is that right? 196. You're right. I got my 6 and my 9 backwards, didn't I? Okay. So I actually get x squared plus 28x plus 196. Okay, so I can bring that right down here. I have x squared plus 28x plus 196. Now, how am I going to go about solving that? Because usually what we've done, we haven't had an x squared and an x at the same time, because those are different variables, right? What should I do? Yeah, let's go ahead and start combining like terms and see what happens. So we want to move this x squared over here, right? So I subtract x squared, I still have 784 equals, well, yeah, what happened here? Yeah, they canceled on both sides, didn't they? So I have 28x plus 196. Subtract 196. Thank you. I get 588 equals 28x. X equals 21. Okay. So, what's the label on that, though? Feet. So what did I just find right there? What were we talking about? No. The radius of what? Right. So you just found the radius of something that you couldn't get inside and find, right? Okay. So just a small example. You can find the radius of things without actually being able to even get inside of it. Okay, I think the example your book used was a grain bin. Okay. Again, no homework tonight. We'll finish this up and work on that tomorrow.